Good afternoon, everyone. Welcome. Today we have we have the pleasure of having two of the best black hole scientists in 2 consecutive days. Daryl Haggard yesterday and Erin today. Erin is a professor at MIT, and she's also a part of a whole range of missions. She's the deputy principal investigator of the AXIS probe mission. She's part of XRISM, Ultrasat, and also recently of LISA. So she has a whole lot of interesting things to say about black holes, I'm sure. She did her BA at the Barnard College, Columbia, a PhD in Cambridge in the UK, and then she was a Hubble Fellow and a JSI Fellow at Maryland before moving to MIT. Erin is one of my favorite black hole scientists, so yeah, enjoy her talk.
All right, thank you. All right, thank you so much. And I have to say that Bart is one of my favorite black hole theorists. So yeah, it's really been a wonderful day. Thank you so much for inviting me to be here. Yeah, I'm going to tell you a little bit about the work we've been doing recently on black hole accretion and black hole growth in the time domain and multi-messenger era. So let's start off with a little bit of motivation for studying these systems. This is an image from the James Webb Space Telescope, and James Webb and Hubble before it was really amazing at finding all of these galaxies in this image, some very in the nearby universe, some when the universe was only just a few 100 million years old. And I remember when I first saw like that Hubble deep field image, the thing that kind of blew me away was that there are supermassive black holes sitting at the centers of all of those massive galaxies. Supermassive black holes that are 1 million to 1 billion times the mass of the sun. And now what James Webb is discovering are these candidate quasars, these supermassive black holes that formed in the very, very early universe, really when the universe was only a few 100 million years old, and yet we're still seeing some of the biggest black holes that we know of in the entire universe. And so that begs the question of like, how do you form a supermassive black hole in the first place, and how do you grow it so fast in the early universe? So how do black holes grow to be so big? How do they form in the first place? So a lot of that growth is happening from material from that surrounding host galaxy that makes its way down to the inner regions of the black hole and grows this black hole via accretion over time. Also, we can have black holes that merge together and form bigger black holes, but this accretion process is the primary means for growing these black holes. Accretion onto a black hole is not a quiet process. What we know is that so much of the energy is actually released into the system, and so it makes it that these black holes are, when they're actively accreting, they are the most luminous objects in the universe. So this accretion produces these luminous quasars that can completely outshine all of the stars in the galaxy, like in this example here. And we also know that supermassive black holes can launch these relativistic jets. This is one of my favorite images of a cluster of galaxies. And you can see the blue there is showing you the hot gas revealed via X-ray observations. That's the hot gas between all of these different galaxies. And at the center is the brightest cluster galaxy that has a massive quasar at its center. And it's releasing, ejecting these relativistic jets that you see via synchrotron emission in the pink there. And what's so cool about looking at clusters is that you can see, perhaps you can see this kind of cavity in the blue hot gas that these jets are just punching out, the hot gas or permeating this cluster. And so really what this is kind of saying in the most dramatic fashion is that this tiny, puny little black hole compared to the galaxies in which it resides can really affect large scales of the galaxies. So we want to understand, not only how do black holes grow, via accretion. But how does then that accretion process release all of this energy in the form of radiation and relativistic jets and wide-scale outflows that can affect the galaxy on large scales and really kind of determines how galaxies evolve? And so, what I'm interested in is how are these outflows powered? And if we want to understand, how does accretion then lead to this ejection, we want to zoom into the innermost regions where most of the energy is being released. So in these accreting black holes, most of the power is being output within like 20 gravitational radii, or even smaller scales if that black hole is rapidly rotating. And so this is the goal of my research, is kind of understanding the innermost regions of these actively accreting black holes. So Daryl yesterday was telling you about Sagittarius A star and M87, these very low accretion rate objects where EHT can even spatially resolve these. Now we're talking about the actively growing black holes when they're accreting at 1 to 100% of the Eddington limit. So if we could zoom into these innermost regions and resolve them, we would see matter flowing in towards the black hole via an accretion disk. And what we see ubiquitous in all of these systems as well is that they produce copious amounts of X-ray emission. And really this X-ray emission is coming, the disk itself is hot enough to emit black body radiation in the ultraviolet band and into the EUV. A lot of that emission from the disk is not observable to, emitted in the EUV, so we can't really see it. But what we can see in all of these systems is that they are very luminous in X-rays. And this X-ray emission comes from some hot plasma, billion-degree plasma around the black hole that we call the X-ray corona. And because X-rays, can penetrate through, the ISM of the galaxy, we can see it in all of these systems, and it is our probe of the very innermost regions of these actively accreting systems. And so that allows us, looking at the X-ray emission really allows us to constrain what's the geometry of like how material flows into the black hole and how energy is released in the form of radiation and outflows. One of the other things that we can probe and measure with these X-ray observations are fundamental properties of the black holes themselves, the mass, and namely the spin. So spin is a really important, parameter if you're interested, of course, in, for instance, testing general relativity. I would say at least you better be able to measure the mass and spin of your black hole. But even if you really are interested in the astrophysics of these systems, the spin, it actually dictates, a lot of how these systems behave and can tell us about how they grew and how they launched these jets. So, perhaps, via the Blandford-Sanayak mechanism, it is this, you're tapping the spin energy of the black hole to produce these relativistic jets. The spin also tells you, what's your radiative efficiency for the amount of material that you're accreting in, how much radiation are you getting out? That's very sensitive to the spin of the black hole. And if you can measure spin in, for instance, in a wide range of objects, it tells you something about how these black holes grew. So this is something that Maya Fischbach has been working on a lot in explaining how black hole spin affects, what's the effect on black hole spin and how does that help us inform the formation of stellar mass black hole systems. But you can also do a similar game with supermassive black hole systems. For instance, if we can measure spin distributions across a wide range of sources in the local universe, and we see that, for instance, they're largely maximally rotating, that tells you that, this is like what we predict for a growth scenario where these black holes were grown via prolonged accretion through an accretion disk. As that material accretes onto the black hole, it eventually spins it up over time, and you should see, more highly rotating black holes. Whereas if black holes grew just from mergers, you should expect more of a uniform spin distribution. So measuring the spin of the black hole and probing these innermost regions are really helping us to get at these questions of how black holes grow and how they affect their environments. So in my work, I'm interested in kind of black hole growth across all sorts of kinds of systems. And we want to understand how do these, I motivated this really to understand how supermassive black holes grow, how we explain these active galactic nuclei, these actively growing black holes. The same is true for, we want to understand stellar mass black holes that are in companion systems with normal stars, and they're accreting material off of the stars. I think of these kind of as like scaled down versions of the supermassive black holes, whereas these things turn on and off on timescales of maybe 10 million years. Well, in the X-ray binaries, the equivalent timescale, they turn on and off on like a few months. So they're just kind of convenient systems for studying the formation of an accretion disk and the launching of relativistic jets. But what I want to focus on today is, these extreme transients that I would say are really, is opening up a new window in what we thought that we understood about black hole accretion and growth. Now, with the advent of optical and really panchromatic multi-wavelength time domain surveys that are monitoring, the entire sky every couple of days or so, we're really revealing like what these black holes were doing when we weren't watching them. Mostly we have just like we point our telescopes at an AGN, and then we think we know what's going on. Maybe we go back and look at that same AGN a few years later. But now we're monitoring all, the entire sky, and it's really kind of, there's just some amazing puzzles that are showing a really extreme black hole transients. And I'd like to tell you a little bit about those puzzles and what we can use these extreme transients for to understand, these greater pictures of black hole growth and accretion. I should say, if there are questions at any point, please shout them out. All right, so I'm going to start with telling you about tidal disruption events, and we'll move then on to a new phenomenon that's really just been discovered in the past, like in 2019, that I think is really taking the time domain community by storm, called these quasi-periodic eruptions. And they may be associated with extreme mass ratio inspirals detectable by LISA. Okay, so first, tidal disruption events. So a tidal disruption event is the system where a star, could be a sun-like star, gets too close to a supermassive black hole. This is a hydro simulation, and this is the early schematic from Martin Rees's 1988 paper theorizing these systems. You have a supermassive black hole here, and a star comes in at some point, at some radius, called the tidal disruption radius. The tidal forces of the black hole will exceed the self-gravity holding that star together. The star will get ripped apart, and some of that stellar material will continue on its trajectory, but about half of that material is bound to the black hole and will fall back towards the black hole, eventually accreting onto the black hole. And so in these systems, they're really, people got really excited about them because it could be a tool for finding black holes that were previously quiescent. Black holes are in fact black if they are not accreting any material, right? And so the only information that we really have about black holes are when they're accreting some kind of gas, right? At least for now. And so these tidal disruption events offered this unique opportunity because you took a quiescent black hole that we didn't really know much about, and now you've thrown a lot of material in it, it suddenly becomes very bright. And so we can measure things like the mass, the spin, et cetera. So that's why people are excited about TDE. What's one of the reasons people are excited about TDEs? And I would say there's been a lot of promise in the field, one thing we want to do is we want to use these TDEs to find missing populations of black holes, previously quiescent black holes. We want to, one of the, I think, really exciting prospects are finding perhaps intermediate mass black holes. And I've told you about stellar mass black holes that are the result of the collapse of a massive star, something around 10 to 100 solar masses. And of course, we also have the supermassive black holes, 10 to the 6 to 10 to the 10 solar masses. But what about in between? Where are these 1,000 solar mass objects? If these supermassive black holes grew from accretion, like from these stellar mass up to supermassive black holes, shouldn't we be finding also intermediate mass black holes? Maybe tidal disruption events, maybe they're just not accreting material. And so if a tidal disruption event happened, you could use that to find this missing population of IMBHs. One of the other interesting ways of using TDEs is that you can probe how accretion happens. In principle, they're like these beautiful systems, like where you have an impulse of accretion, right? We know that half a star is what accreted onto this system. That's like, should be relatively clean, right? And then you can watch, okay, how quickly does a disk form? How quickly does a corona form? How quickly does a jet form? You can watch this happening in real time. And then you can say, oh, when do these things turn off after that material has accreted onto the black hole? That would be like a lovely way of using these black holes. And they've also been suggested to be multi-messenger candidates. There's been some claims that high energy neutrinos are associated with TDE flares, but I would say that's pretty speculative at this point. So how do we find TDEs? Well, TDEs are, we know of about 150 of these systems now. And the way that they've historically been found is a previously quiescent galaxy that suddenly becomes very bright, like becomes the same luminosity as a bright AGN. And its light curve, its luminosity over time, shows this characteristic fast rise. This is just for a number of these sources now. A fast rise as that stellar debris falls back towards the black hole. And then a decay as t to the minus 5/3. This is the theoretical rate of that fallback rate. And for the most part, this is how people have been finding TDEs in large scale surveys. A previously quiescent galaxy that then shows this flare, this kind of characteristic fast rise and power law decay. In the X-ray band, which is my wavelength of choice, I would say, these systems look very different from typical accreting black holes. Here's a compilation of just 4 accreting black holes, 3 AGN that you see in the blue and purple and pink shades here. And they all show high energy X-ray emission from this corona, this hot billion-degree plasma around the black hole. That seems to be universal in all accreting black holes. And these tidal disruption events, when we find a quiescent galaxy that has this characteristic light curve shape, these tidal disruption events don't show the high energy non-thermal emission from the corona. Instead, all you really see is like a black body spectrum from a newly formed accretion disk around this like 10 to the 6 solar mass black hole. So why they don't show coronae, why they don't produce this billion-degree plasma is exactly why I'm here, and Bart's going to solve that for me. Yeah. So, but needless to say, this is now like an observational fact that a lot of these tidal disruption event systems, at early times at least, do not show coronae, and we can use this kind of as a way to say, okay, that wasn't just some crazy flare from an AGN, from a persistently accreting black hole. It really is something different. It's a tidal disruption event. So now with these multi-wavelength approaches, we have been able to find about 150 or so. This is now a couple of years out of date, but we have about 150 of these systems. And so one of the things that you would love to use tidal disruption events for is if you could like measure their rates and measure their rates as a function of black hole mass. This could tell you something about the spin demographics of black holes. So for instance, like if you have, if this is your notional distribution of black holes, right? You could compare that to your measured distribution of tidal disruption events, and that will tell you something about the black hole spin. And that's because eventually, as you should preferentially get these tidal disruption events happening in lower mass, million solar mass black holes, because eventually, as you go to larger and larger masses, your event horizon radius is going, your inner edge of your accretion disk scales with the mass of the black hole. It's growing faster than the tidal disruption radius. And at some point, that event horizon is going to be outside of the tidal disruption radius. So a star coming in won't get disrupted at all. It'll just plunge right past and plunge directly into the black hole. So you really should see a dearth of tidal disruption events happening in very massive systems. And the only way that you really should be able to get TDEs from normal stars in very high mass systems is if you spin up that black hole, and then frame dragging effects are going to support more orbits closer to the black hole, and your ISCO, your innermost stable circular orbit, moves in. And then you'll be able to have tidal disruption events happening only in these rapidly rotating black holes. So this is one of the things that people would love to be able to do if you understood your observational biases perfectly well. You could, in principle, use TDEs to measure black hole spin demographics. The question is and indeed, actually, we do see more TDEs in lower mass black holes. And the question is now, what kind of selection biases are there? So we wanted to understand our observational biases. Most of the TDEs that we discover now are in the optical band, thanks because we have these amazing optical time domain surveys, or in the X-ray band. And we wanted to see, can we understand, the observational effects? Can we look for TDEs at other wavelengths, and in particular in the mid-infrared? So perhaps, we're missing populations by finding these things only in the optical band. If there's a lot of gas in that galaxy, a lot of dust in that galaxy, you could be totally, missing. There could be lots of extinction, and you'd miss all of your optical flares. So maybe there actually could be a lot more TDEs, except we're missing them because we're looking in the wrong waveband. And indeed, I should say that we observationally, we predict, theoretically, we predict, if you calculate the number of stars that should enter the loss cone of the black hole for a given, density distribution, we should expect about, 10 to the minus 4 TDEs per galaxy per year. And yet when we look in the optical, we're about an order of magnitude less than that. So we're missing tidal disruption events by looking in the optical. And the question is this physical, or is this some observational bias? So we decided to take this on by looking in the mid-infrared. And this is work with Kishalay Day, who's an Einstein Fellow at MIT, soon to start a faculty position at Columbia. He's a mid-infrared astronomer, and he made a WISE difference. WISE is an all-sky mid-infrared survey, and he did difference imaging on the entire WISE survey, and worked with Christos Panagiotou, a postdoc at MIT, and my student Megan Masterson on using this survey to find previously unknown tidal disruption events in the mid-infrared band. So this is one of the early observations that came out from this search. was the nearest TDE to date at only 42 megaparsecs, like really in our solar neighborhood, in our backyard. And what you can see, these points here are the mid-infrared. It was a previously undetected source, no prior AGN activity, became extremely bright, and decayed as this T to the minus 5/3. And that said to us, that's the signature of a TDE. But the optical, all of these are upper limits from the optical, even though this source, this is such a nearby object, no optical surveys could see it. There's so much dust in the way that all that we could see, you don't see any optical, all you see is reprocessed, the dust that emits in the infrared band. Megan Masterson, fifth-year PhD student in my group, really has extended this now and did an extremely careful analysis of all of the flares within 200 megaparsecs, so still pretty local universe, and discovered a whole bunch more of these systems that show this fast rise and slow decay. And again, all of these are optical upper limits, not a signature of in the optical. So we were missing this population by not looking in the mid-infrared. So this doubles the rate of known TDEs in the local universe and really is getting us a little bit closer to at least that theoretical rate, and at least helping us kind of understand our observational biases in these systems, hopefully getting us a little bit closer to that promise of TDEs. It also, for people who study TDEs, solves other problems too. Like for instance, it was a big puzzle in the field that these systems, these TDEs occurred in a very unique population of host galaxies, post-starburst galaxies that are like 0.2% of all of the galaxies that we know of. And yet many, many TDEs were happening in these post-starburst. Well, perhaps we don't find that any of these are happening in post-starburst galaxies, which is telling us that at least some of that result was an observational bias. Okay, so moving on now to a very particular special case of a tidal disruption event. This is not mid-infrared selected, just regular old X-ray selected tidal disruption event. This is one that we've known of for many years now, but became extra special in 2019. So again, it was in archival observations. The X-rays showed nothing, no hard X-rays indicative of an actively, a quasar or anything, an actively growing black hole, a persistently accreting black hole, but then suddenly became very bright and decayed slowly over time. So this is telling us, this is like a good indicator that this system might be related to a tidal disruption event. A few years after the initial flare, XMM observed this source, and it showed, not much. Just kind of the brightness, the luminosity over time was flat, not very interesting. And when we observed the system again several years later, we saw something very different. Quasi-periodic flares happening every few hours in this system. And I'll tell you, I was at a conference when this was first announced, and it was like the most amazing feeling. We were all shocked because this is not, AGN show stochastically random variability, or they don't show much at all in these tidal disruption events. But this was it blew all of our minds. For a little while I thought maybe it's like a pulsar in our line of sight, but no, it's really not. It is associated with the galaxy. And not only are we seeing it in this one candidate, now we have 8 QPE candidates. And they all show systems like this, flares every few hours to every few days. And interestingly, they all seem to show no corona. So again, like these other tidal disruption events that are different from persistently accreting black holes, that they showed no high energy X-ray emission. They only look like a thermal disk emission that becomes suddenly very bright every few hours. I first got into TDEs working with Johin Chakraborty, who is a third-year PhD student in my group. And we said, okay, well, that was like an incredible discovery, GSN 069. But this was using a telescope that had been in orbit for like 20 years at that point. And so were we missing? Have we been missing these quasi-periodic eruptions just because we didn't know to look for them? And so what we did with Johin was to look back through the XMM Newton archive and employ an algorithm used by the exoplanet community for finding exoplanet transits. And Johin had this great idea that, what is an exoplanet transit but a quasi-periodic eruption upside down? And so what we did was apply this algorithm, and we found one more candidate quasi-periodic eruption. And it's 2 flares, which is a little disappointing. It's only 2 flares. But it also shows only a thermal blackbody spectrum, no high energy X-rays. And interestingly, this was the second QPE coincident with a tidal disruption event, which told us, again, gave us confidence that these really are kind of similar systems. Our takeaway from this was that maybe that these QPEs are rare, but also that we clearly were not monitoring these sources long enough to be able to find these flares that happen every couple of hours. I would say now it's, as of a couple of weeks ago, this is a paper that's actually just recently been accepted in Nature, that now it is unambiguous that these quasi-periodic eruptions happen in some tidal disruption events. This is an optically selected tidal disruption event, a totally bona fide tidal disruption event that several years after the peak emission, peak outburst, suddenly started showing these quasi-periodic eruptions. So the question now that is plaguing the field is, what the heck are they? And I would say there are more theories that have come out in the past few years than there are QPE candidates, by maybe an order of magnitude. And we hope to change that, but this is the state of the field right now. So basically lots of models have come out, but I would say they are generally in like 2 distinct classes. One is that there's some disk instability happening in these systems. We don't understand how luminous accretion disks really work. And while most of the time they show, stochastic variability, perhaps you could have some radiation pressure instability that causes these kind of periodic flares or quasi-periodic flares. The other class of models, and I would say is the class of models that's getting more attention these days, are that perhaps what we're seeing is an Embry-based model, an extreme mass ratio inspiral, a supermassive black hole with a stellar mass companion orbiting around it. And what I'll say is that these Embry models are appealing, especially for some of these QPE sources, because they show, some of them show they're quasi-periodic. They're not totally periodic. They show short, long behavior in their flares. And in an Embry model, this is kind of an appealing picture. Let's say you have your supermassive black hole, you have an accretion disk around it. As if this Embry is on a mildly elliptical orbit, it's crashing into this disk twice every orbit, creating this impulse, this flare, twice every orbit. But if it's on a mildly eccentric orbit, that might explain why you get, this long and then short, long, short behavior. In amplitude, yes, right. So maybe you're seeing, as the QP, the object, it comes, if you're observing from this side, maybe it'll be brighter as it enters and dimmer as it goes back, on the other side of the disk. So it kind of is an appealing picture, but unfortunately, it doesn't fit. Not all QPEs show this really long, beautiful, kind of deterministic, almost long, short behavior. And in particular, this one source, EuroQPE1, found by Riccardo Arcodia during his PhD with the eRosita collaboration. He found this QPE that we've now been monitoring for 4 years with the LISA Observatory. And it was always a puzzle. It didn't show this beautiful long short behavior. Sometimes it showed double flares, and the flare amplitudes are kind of all over the place. And so Joachim now has been monitoring this and maybe perhaps has put some order to the chaos. What Joachim realized is that, perhaps these flares, it's not just that they're coming at random times. The arrival time seems to be modulated on a 6-day period. So we're seeing flares, these QPEs, roughly every day, but the arrival time is modulated by a 6-day superorbital period. I would say this is still pretty tentative, but I think it's a great, it's like kind of where we need to go to be able to, understand these timing properties. So, perhaps rather conveniently, this 6-day superorbital timescale could be associated with like a lens-Turing precession timescale. If this underlying accretion disk is precessing, sometimes you catch the emery interacts with the disk earlier than you expect, and sometimes it interacts later. And so perhaps that can explain this 6-day superorbital period. So I would say this is still pretty tentative. You always have to be careful when you're talking about quasi-periodicities, but it's the direction that we need to go in order to really decipher between these two models. What I will say, what's nice about the emery model is that there are predictions that we can test with future flares. If we create a waveform that describes the flares, then we can test it on future observations. And so I would just say, while I think we still don't know if disk instabilities couldn't be the solution, what we're really lacking are testable predictions to see if it can make this work. Okay. So in the last few minutes, I want to tell you about one last tidal disruption event candidate. This is my favorite source in the sky. And it's the source that it keeps on surprising us. So this is 1ES 1927. It was a known AGN. 1ES, ES is means Einstein telescope. Einstein from the Einstein telescope from the 80s or whatever. So it's like a known AGN from way back when. And in 2018, the Assassin All-Sky Optical Time Domain Survey found a very massive flare. And it looks like all of those TDEs, fast rise over a couple months and a slow decline in the optical. What was cool about this was that it was a known X-ray source, a known AGN, and it had archival observations, really nice archival observations, which we don't typically have of these TDEs. And it looked like a regular AGN. It showed that hard X-ray corona that I said is ubiquitous in persistently accreting black holes. After the flare happened in the optical, we got follow-up observations, and this is what they looked like. Basically, that corona, that hot billion-degree plasma just disappeared. And all that was left was this kind of quasi-thermal-like spectrum, reminiscent of TDEs. And so we posited that this could be a tidal disruption event happening in a previous AGN system. And they should happen in AGN as well, right? It's just a star comes into your into your nuclear environments. Even if that's an AGN, they should also show TDEs. So this system became, this was our follow-up observations. The red here is the spectrum that you see here. We followed it up with NICER as well, and you can see it's highly variable. And it then started to decline the first 50 days. And this is 4 orders of magnitude. it declined. It became basically quiescent. It went from like some full-fledged AGN luminosity down to like a quiescent galaxy in timescales of like 50 days, which isn't totally crazy for a tidal disruption event. And we started like not detecting it anymore. And we thought, okay, that was like a nice go. It was fun to watch that happen. But then thankfully we kept monitoring it because it came back with a vengeance. And it actually was like the brightest X-ray source in the sky for a couple of years. And it became extremely bright and extremely variable. And as we watched it come back over time, that hard X-ray corona component started to rebuild over time. So I said, we don't know what powers the corona. We don't know how it gets to be so hot, how it forms in the first place. And here are observations of a source where we're actually watching a corona form in real time. So we got pretty excited about this. Perhaps a TDE has come in to this previous AGN system, disrupted whatever magnetic field structure is required to produce a corona in the first place. It shut the corona off, and now we're watching that corona rebuild itself as the magnetic flux, kind of accumulates over time. It has, that's right. So actually, there's so much that I could say about this. This is a black body, but there's also like, this is sharper. This is like not just like the bean tail, it's sharper than that. And actually it's, you need an additional broad emission line component that we don't really know what it's due to, but we attribute to an ultra fast outflow that we can talk more about.
Then when you put that up, that's not that.
Oh, exactly. That's what I'm saying. Yeah, exactly. It's not a black body. Yeah, that you cannot model that simply as a black body. It has a hard non-thermal tail. So that's what why we said that the corona is turning back on over time. And eventually, actually, as we continue to monitor this source, it kind of settled back down into its pre-outburst flux spectrum. Yeah. Cool. So we learned to not take our eye off of this object because it was very surprising. And so we've been monitoring it regularly over the past couple of years. And honestly, I was like kind of getting a little bored of it because, it did this amazing outburst. It hit the Eddington limit. This dashed line is the Eddington limit for a 10 to the 6 solar mass black hole. And it just parked there for a year. But then, it has been gurgling along these past couple of years. But, recently we took a closer look at the observations for the last couple of years. And what we found was a quasi-periodic oscillation. And this is like, AGN don't typically show this. There are 2 AGN that have quasi-periodic oscillations. And, sometimes you'll hear like claims of a QPO. They're hard to measure if you don't have many cycles, but this is like 50 or 100 cycles. Like this is a sure thing, many sigma detection of a quasi-periodic oscillation. And this is it's a millihertz oscillation. And so what we got excited about was that millihertz oscillations is like, 10 minutes or so. Is this system like similar to these quasi-periodic eruptions where we see flares every couple of hours? This system is very similar in that it is a tidal disruption event associated with or some kind of extreme nuclear transient. They only happen in low mass black holes, super soft X-ray spectra, and the periodic behavior only begins several years after the initial outburst. So I think that even though these are very different timescales, they occur in very similar systems. And what if they are indeed related somehow? That would make it really exciting because if these quasi-periodic eruptions, 8 hours for a 10 to the 6 solar mass black hole would put this at an orbit at like hundreds of gravitational radii. In this 10-minute system, that would put you at orbital timescales of like orbital radius of 10 RG. And so, you know, in these, it's really hard for both of these models to explain such rapid quasi-periodic variability. And if it's an orbiter, it's happening extremely close to the black hole. And in fact, if our mass estimate is correct, that this is a 10 to the 6 solar mass black hole, in fact, these oscillations are so fast that this needs to be a rapidly rotating black hole, or else it would be within the ISCO. So we have to explain, how do we get these oscillations? How do they persist for 2 years if they are also so close to the black hole? And what's even more exciting is that we didn't just measure it once, but we measured it many times. And the QPO frequency is evolving in time. And at first, it goes from something like 18-minute period to a 7-minute period. At first, we saw these 2 observations. We saw the QPO in these 2 observations, and we're like, whoa, that's amazing. If this is due to orbital motion, like, you're definitely in the gravitational wave-driven regime. And at some point, you know, this evolution should be dictated by GR, and we can make a prediction for when the orbiter should plunge into the black hole. And so we made a prediction, February 24th, 2024, we should no longer see this QPO if it's a gravitational wave event. But of course, then we did measure it, black hole. This is the predictions from GR for different mass companions. But you know, of course, they all should just speed up as you lose energy from gravitational waves. And what we found when we got those observations was it was a little bit of a letdown, but the QPO was still there. It was still strong, but it was at 7 minutes now. And we have follow-up observations now, even later, that showed that it's really parked at like 2.7 millihertz, something millihertz. And so, you know, if this is an orbiter model, how do you explain it? You know, it's not just GR, but also you have an accretion disk. So gas drag effects would even speed this evolution up even faster. And so if we wanted to you know, keep this orbiter model alive, you need to have some way to maybe mass transfer. Maybe this companion is like a white dwarf system that's mass transferring onto the supermassive black hole, and that could stall this, you know, in spiral. So on the other hand, if this is some kind of you know, instability, it's still happening extremely close to the horizon, and it's also very hard for those known models to persist over 2 years. So I would say all these amazing theorists here at CETA, please figure it out for us. If this is an EMRI, an orbiter, what's awesome is that it is LISA detectable. It's in the millihertz range, and this source is only at like 80 megaparsecs, very nearby. And so it would produce a strain that's observable with LISA. So that's really our prediction, is that in 2035 or whatever, when LISA flies, if we're right about this white dwarf model, we'll see it. So this is kind of exciting that, you know, this is a provocative plot. If indeed these quasi-periodic eruptions are due to an orbiter, these are the kinds of, this is where they might be LISA detectable. And hopefully we'll find many more of these. And this 1ES1927 is right smack in the middle of the LISA sensitivity band. Okay, now I'd like to end my talk, but before I do, it is 30 seconds to 4 o'clock right now. And so I feel like I can tell you about the future of this field. We have been Daryl and several of us have been working on the future X-ray observatory. This is a NASA probe mission concept called AXIS. We see it as a kind of super Chandra or super swift XRT. It's like Chandra, but 10 times the sensitivity and with fast slew capabilities. So it's really perfect for monitoring things like tidal disruption events and quasi-periodic eruptions. It's also great for finding the first, you know, the X-ray counterparts of those first quasars at a redshift of 10. And we just found out that this is has been under consideration by NASA for the past year. We submitted a proposal, and right now it's 4 o'clock. And so I can tell you NASA is releasing a press release that we've made it to a phase A study. We're in a finalist phase A study. So keep your fingers crossed. In the next year, we're going to be working to show that we can actually build this thing and hopefully see it fly in 2032. So I will leave you with my summary and take any questions. Thanks.